Hello there and welcome back to this video series on control systems. We have seen that root locus is the way in which the roots move in the S-plane as one particular parameter, which we call gain, is varied from 0 to infinity, that is very small values to very large values. We have seen that by observing the open loop transfer function, we can predict and plot the root locus effectively just by looking at poles and zeros of open loop transfer function. We have seen rules given by events for constructing this root locus. In this video, we will try to solve two examples. And so we can say as outcomes, you will be able to draw the root locus plot for relatively simple transfer functions without too big complications. I would strongly encourage you to watch through videos 43, 44, 45, definitely before watching this video, because you will be making the most out of this video if you do that, and if you familiarize yourself with complex numbers and finding angles and so on, it would be wonderful. With that, we'll continue into example 1, where we look at a unity feedback control system with the loop transfer function given over here. The first step or first rule is to identify number of zeros. There is no polynomial in the numerator, so there are no zeros. M is equal to 0, and if you equate the denominator to 0, you'll find 3 poles. S is equal to 0, -1 and -2. So this we call P1, P2 and P3. So N is equal to 3. M is equal to 0. So N minus M, 3 minus 0, there are 3 asymptotes. We'll note this and go to rule 2. We'll show the poles P1, P2 and P3, and then note that one branch starts at P1 and has to go towards the left, one branch starts at P2 and has to go towards the right, and one branch has to start at P3 and go towards the left. Okay, we'll exactly show those. One branch begins and comes this way, another branch begins and comes this way. They both meet at breakaway point and get separated, and then the third branch keeps on going. As k tends to infinity, this will also tend to infinity. Okay, and then we will go on to rule 3, that is asymptotes. Again, we will show poles P1, P2, P3, and we say that this sigma P minus sigma Z, that is 0 plus -1 plus -2 divided by 3 is -1. So all the asymptotes meet at this point, and the angles are 60, 80 and 300. Let us show these. One asymptote is at 60 degrees, so this is the asymptote A1, which is making an angle 60 degrees, and then another asymptote is making angle 180 degrees. A2 is shown here, and third asymptote is making 300 degrees, because if you look at it, this whole angle measured in counterclockwise direction is 300. We can also show it as -60. With that noted, we'll go on to rule 4. We'll find breakaway point. To find breakaway point, you differentiate this with respect to S and equate it to 0, and that gives us this quadratic equation, 2 roots -0.42 and -0.17. We know the breakaway point lies between 0 and 1, because this comes here, this comes here, they collide and they get separated. So this is the breakaway point. So we'll choose the one between 0 and -1, and we reject the other. This other one is the breakaway point for the complementary root locus. We are not concerned with that right now, and we will go on to the next step. Rule 5, angle of arrival and departure, does not apply here. This rule 5 applies only in cases where you have either poles or zeros away from real axis, that is complex poles or zeros. With that, we go on to the next rule, that is intersection with imaginary axis. So we write the characteristic equation and we build a routes array 1 and 2, then 3 and k. Then the next row is 6 minus k over 3. Then the next row is k. So we say that for stability, all the values here must be positive. So the range is 0 less than k less than 6. K has to be greater than 0 because this has to be positive. K has to be less than 6 because this has to be positive. So 0 less than k less than 6 is the region of stability. If you substitute k is equal to 6, 6 minus k divided by 3 is 0. So you have an entire row of zeros. The row above this row of zeros contains auxiliary polynomial, which is 3s square plus 6, okay, that is s square plus 2. That gives s is equal to plus or minus root 2j. So omega is root 2. You plot root 2 here and then root 2 here, and this gives us 3 points, point here, and point here, through which we can draw a smooth graph in such a way that it gradually coincides with A1. So that is what we will try to draw a smooth curve going through the 3 points and going to infinity. With that, we need to find the value of k and conclude the problem. Point s is equal to minus 0.42, minus 0.42 minus pole p1 0, minus 0.42 minus of minus 1 plus pole p2, again minus 0.42 minus of minus 2 is plus. So if you do all that, you get 0.38. So that we indicate 0.38 is the gain at the breakaway point. Now that we are familiar with the rules, we'll quickly go over another example where GS is given to be a rational expression given here. We see that there are two zeros, minus 1, minus 5, and two poles, minus 4 plus 3j, minus 4 minus 3j. Because m is equal to 2 and n is equal to 2, there are no asymptotes. And we plot these poles and zeros on S plane as shown over here. P1, P2 are there, this Z1, Z2 are there. And on the real axis, you don't have any root here, you have root here, you don't have any root here. You have a break in point because one branch of root locus has to begin at P1 and go to either Z1 or Z2. Another branch has to start at P2 and go to either Z1 or Z2. If this branch goes to Z1, this branch starting goes to Z2, and so on. So we find the derivative of gs and equate it to 0, and you see that it's obviously not minus 16.70. It has to break in somewhere between minus 1 and minus 5. So we accept this and reject this. We'll note this as the break in point. Okay. The next one is a little bit tricky, but let me go slowly at it. You have this as the angle criterion. Sum of angles of poles minus sum of angles of s minus zeros is 180 degrees. We say to find the angle of departure here, angle of departure is the tangent, angle of the tangent to the curve at P1. So we say S tends to P1 and S minus P1 tends to phi of A. phi of A or phi of B. Okay, so phi A plus angle P1 minus P2 minus P1 minus Z1 plus P1 minus Z2. All we are doing is substituting S is equal to P1 in this equation, and in the place of P1 minus P1 you put phi. Evaluate, and it's shown to be 296.56. 296.56 is given over here. Okay, the corresponding angle is minus 297.56 here because poles P1 and P2 are conjugate. So we'll show this angle here. Minus 63.44 is the angle of departure here, plus 63.44 is the angle of departure here. So you draw a smooth curve which is tangent to this, and passes through this point. So you obtain this curve. You can see it's not intersecting with imaginary axis. That is why we didn't apply rule 6 here. So the only thing that you need to find perhaps is the gain at this point. S is equal to minus 3.29. So to find the gain, substitute K is equal to magnitudes of S minus P1 and S minus P2 divided by so on and so forth. You substitute S is equal to minus 3.29, P1, P2 values. You find K is equal to 2.42. You indicate that here, and the root locus plot is complete. We see that whatever be the value of K, even if you increase K unboundedly, the roots are always stable because they are not migrating anywhere. With that, we'll summarize. We'll summarize by saying that root locus plot shows how the roots move in the S-plane as one parameter is varied from 0 to infinity. The method given by Walter Evans gives us a very easy way to draw root locus plots using simple rules. There are 6 in number, but we need not always use all of them. If there are no points of intersection with imaginary axis, you don't use that rule. If there are no complex poles or zeros, we don't use that rule. I think that's all we have for now. Have a great day.